You guys remember that? What is that?
48.
Okay. Yeah, this is called Fourier transform. Okay, this is what a noisy image looks like. Okay? There's 64 pixels here. There's 64 going in the vertical, there's 64 going in the horizontal. I just told the computer, just look at this row of pixels that are passing through my object. Okay? This is my object here. So if I was to subject this to a low pass, now this tells me the maximum number of counts. Okay, 68. So that means that most of these counts are somewhere between maybe 5 to 30 per pixel. You go through that. Can you even see the object? If this thing wasn't here, can you see that there was an object there? You see that there's a decrease there, so maybe there's something there. This is the actual video signal that goes to your computer. The computer is going to divide this up into 64 equal slices. Whatever the voltage is there, that's the number that gets recorded in that address. If I made it 128, all of these pulses are the same duration. So if I go to 128 by 128, I'm going to divide this into 128 equal time segments, and then that's going to represent this image on my computer. Let's see, this is what smoothing does. You can either accomplish that by the filtration using the low-pass filter, or you can simply go for more counts. Look at that, 2,856 counts. Basically, now you can see that there's something obviously here. And what I did with this thing here is I just widened the area that I was looking at. Remember, this is why you go to a 64 by 64 matrix. This might be a 256 by 256 matrix, or a low-pass filter. And if I wanted to sharpen this image up, then I would go to a high-pass filter, and that eliminates those long wavelength frequencies, and basically it would eliminate all of this, and all I would have would just be the edges of the object. So it would give me a much sharper definition. Okay. And remember, I told you that this. Okay, this is the electrical signal of my MOV study. Okay, if I started at the top, I would get a different pattern. Well, actually, you can see it here. Let me just widen this up a little bit. So the same image. Okay. Okay. As the image is coming into your computer, it goes in one at a time, or if we use an array processor, then all 64 lines are converted at the same time. But basically, if you drew this anywhere on your image, this is what that three-dimensional information looks like to your computer. This is this one line of information down here. This is the one line of information going through the heart. So as I said over here, as I'm going across, okay, I get to the right. Here's the edge of the right ventricle here. Okay, then the count rate rises. So here's my right ventricle. Okay, then it drops down. There's my septum, and then it continues to the left ventricle. I'm not sure why there's a spike there. If you did gated imaging, this MOV study was not gated. Okay. When we were doing this, we basically just labeled the red blood cells. The computer would do what they call an ejection fraction. It would you draw a region of interest around the left ventricle. The computer would then identify, these drop-offs. We would calculate the slope of this here, and the computer would assign a region of interest based on what they call the second derivation of the slope. So basically it looks at the count rate in this pixel, compares it to the one next to it. That's your first derivation. Then, let's say that there is a difference of 10 counts between the two pixels. That's the first derivation. So I've got 100 counts here. I've got 90 counts next to it. That's the first derivation. To calculate the edge, I would go for the second derivation, and that would be minus another 10. So the first pixel that I come across that has 80 counts in it, the computer says, okay, that's the edge of the heart. Weird, huh? So, but I just wanted you to understand that, okay, when you have, this is noise, okay, this would be a high-pass filter, and basically it gives you a sharp edge, provided you have enough information to have a picture. So, you guys want to take a break for a few minutes?
Yes.
You guys don't need breaks. You don't need to eat. You don't need to sleep. You're nuclear medicine students.
So what was that again? The smaller the matrix, the more statistical info that's in it.
Yeah, you have a more noisy. When you go to a smaller matrix, you have to acquire more counts to make sure that there's enough data in those pixels. Otherwise, you get a noisy image.